Chapter 1.1 Introduction. Food production relies on the availability of resources such as land, fresh water, fossil energy, and nutrients. Kotzen et al. 2018. And current consumption or degradation of these resources exceeds their global regeneration rate. Van Vuren et al. 2010. The concept of planetary boundaries, shown in Figure 1.1, aims to define the environmental limits within which humanity can safely operate with regards to scarce resources. Rockstrom et al. 2009. Figure 1.1. Current status of the control variables for 7 of the planetary boundaries as described by Stefan et al. 2015. The green zone is the safe operating space. The yellow represents the zone of uncertainty, increasing risk. The red is a high-risk zone, and the gray zone boundaries are those that have not yet been quantified. The variables outlined in blue, including land system change, freshwater use, and biochemical flows, indicate the planetary boundaries that aquaponics can have a positive impact on. Biochemical flow boundaries that limit food supply are more stringent than climate change. Stefan et al. 2015. In addition to nutrient recycling, dietary changes and waste prevention are integrally necessary to transform current production. Kotzen et al. 2018, Cahaluoto et al. 2014. Thus, a major global challenge is to shift the growth-based economic model towards a balanced eco-economic paradigm that replaces infinite growth with sustainable development. Burnell, 2016. In order to maintain a balanced paradigm, innovative and more ecologically sound cropping systems are required, such that trade-offs between immediate human needs can be balanced whilst maintaining the capacity of the biosphere to provide the required goods and services. Ehrlich and Hart, 2015. In this context, aquaponics has been identified as a farming approach that, through nutrient and waste recycling, can aid in addressing both planetary boundaries, Figure 1.1, and sustainable development goals, particularly for arid regions or areas with non-arable soils. Goddek and Corner, 2019, Applebaum and Kotzen, 2016, Kotzen and Applebaum, 2010. Aquaponics is also proposed as a solution for using marginal lands in urban areas for food production closer to markets. At one time, largely a backyard technology, Bernstein 2011, aquaponics is now growing rapidly into industrial-scale production as technical improvements in design and practice allow for significantly increased output capacities and production efficiencies. One such area of evolution is in the field of coupled versus decoupled aquaponics systems. Traditional designs for one-loop aquaponic systems comprise both aquaculture and hydroponics units between which water recirculates. In such traditional systems, it is necessary to make compromises to the conditions of both subsystems in terms of pH, temperature, and nutrient concentrations. Goddek et al. 2015, Klaus et al. 2015, see Chapter 7. A decoupled aquaponics system, however, can reduce the need for trade-offs by separating the components, thus allowing the conditions in each subsystem to be optimized. Utilization of sludge digesters is another key way of maximizing efficiency through the reuse of solid wastes. Amarenciano et al. 2017, Goddek et al. 2018, Monsees et al. 2015. Although many of the largest facilities worldwide are still in arid regions, i.e. Arabian Peninsula, Australia, and Sub-Saharan Africa, this technology is also being adopted elsewhere, as design advances have increasingly made aquaponics not just a water-saving enterprise, but also an efficient energy and nutrient recycling system.